Hello everybody. We're going to start talking a little bit about electric current today. Um, so let's go ahead and jump right in. Let's first define a circuit. A circuit is a closed path through which charges flow. Take a picture here, this little cartoon picture of a simple light bulb attached to a battery. This is basically how any flashlight works. You've got some battery, you've got a wire that connects one end of the battery to the light bulb, you've got another wire that connects a different part of that light bulb back to the battery. That closed path allows charge to flow from one end of the battery, from one terminal of the battery, through the wires, through the light bulb, and back to the other end of the battery. That flow of charges is what we define as the current in the battery, or current in the circuit. Now, we're going to note that for the purposes of our descriptions of how current flows, we are always going to consider the current as if it's composed of positive charges. They will flow away from the positive terminal of the battery, around the circuit, and into the negative terminal of the battery. As we've discussed before, positive charges in matter is nominally tied up in the nuclei of atoms, and so it doesn't move anywhere. What's really moving, of course, are electrons. And it works out that if we think about the electron motion, electrons are essentially leaving the battery from the negative end and flowing around in the opposite direction. So, as we've discussed, whether we think of positive charges in one direction or negative charges flowing in the other direction, mathematically it's identical. In any case, that flow of charges is what we define as the current. Now, mathematically, we define the current as a number of charge, an amount of charge passing a point per unit time. So, as an analogy, we could imagine stationing a person outside of a hallway and counting how many people walk down that hallway every minute. When more people are moving down the hallway, there is higher traffic. If you have the same number of people who are running down the hallway, they're moving faster, so they're passing in smaller amounts of time. Again, we have higher traffic, we have a higher current. So really, when we're talking about electrical current, we don't usually worry too much about how much charge there is or how fast it's moving. Rather, we take that as one big piece, some amount of charge passing a point per unit time. The units of charge are amperes, which we symbolize with an A, and an ampere is defined as 1 coulomb per second of current. All right, so let's take a quick example. A light bulb might experience a current of 1/4 of an amp, 0.25 amps. How many electrons flow through that light bulb each second? So if you want to take a minute and go back and look at our definition of current, you can try this for yourself. Pause and we'll take a look here in a second. All right, I assume you're ready to go on. We can solve for that amount of charge from our definition of current. And you can see here that I've taken that current equation and I've rearranged it to solve for the amount of charge delta Q. Again, if you'd like to pause with this hint and complete the problem on your own, please do so now. Okay, so let's take a look and see how I solve this and see if you've gotten the same answer. All I need to do is plug in those values, 1/4 of an amp for the current I, and in one, apparently I changed my example. The mathematics here, I solve for how much current flows through every minute. For each second, how much light bulb flows through the current in a second, the answer, we would multiply that 1/4 of an amp by 1 second to give 1/4 of a coulomb. Clearly, I thought I was solving a different problem. In 1 minute, in 60 seconds, 15 coulombs of current will flow. All right, so how many electrons is that? We're going to go ahead and stick with that 1 minute, flow. the total number of charge is equal, the total amount, the total charge that we measure is equal to the charge of each electron multiplied by the number of electrons. So N is the total number of electrons, E is the charge on each electron, the elementary charge, and so that should be equal to the total charge Q. So if we solve that for N, the total number of electrons, Q, divided by the elementary charge, gives us 15 coulombs divided by 1.602 times 10 to the negative 19th coulombs per electron, which gives me an answer of about 9.4 roughly times 10 to the 19th electrons. So an awful lot of charge is moving through that light bulb over that time. All right, so let's think a little bit about current flow in a conductor. So we're going to take an electron that is in a conductor, and we're going to subject it to an electric field. So we've got a Coulomb force here that looks like QE, where E represents the electric field in that conductor. So we can take that QE and replace it. We can replace the E with the opposite of the change in potential divided by the change in distance. E equals negative delta V over S, or delta V over delta S, sorry, as we've discussed before. Okay, so if that's the only force acting, if the Coulomb force is the only force present, and the electric field is not zero, what does that tell us about the acceleration? Newton's second law says that net force must be equal to the mass times acceleration. If this is the only force and none of the components of this force are zero, that force is not zero, then the acceleration must not be zero either. So this particle must be continually accelerating. The flip side of that, if the velocity of that bit of charge, of that electron, is constant, what can we conclude? And if the velocity is constant, the acceleration must be zero, which means that there has to be some other force acting in the opposite direction of our Coulomb force. There has to be some kind of resistive force or drag force present that is allowing the motion of this charged particle to be constant, allowing the velocity to be constant. So I can write that out like this. The net force is equal to the Coulomb force in one direction minus the drag force in the opposite direction, and those two things have to sum together to be zero. So if I just sort of try to get a feel for what this drag force would have to look like in order to give me a constant velocity, I'm going to substitute my delta V over delta S expression in there. And I'm going to note that a drag force is typically dependent on velocity. So velocity is change in position over change in time. And I'm going to note I've got this change in position thing, but I want to focus on these two parameters. I've got a delta V and I've got a 1 over delta T. And that 1 over delta T makes me think of a current. And I can multiply some constants in here. I can throw some extra Q's in here. That's not the issue. That's not important. What is important is that I have something that looks like, at first glance, a change in potential, a potential difference that is proportional to the current. And in fact, I can lump all those other quantities together and describe that as a single quantity R, what we call the resistance of the conductor, so that I can rewrite that force equation or that force relationship as delta V, the potential difference, is equal to the current multiplied by this other thing, the resistance. We call that equation Ohm's law, and Ohm's law is a valid statement independent of the material, although there's some special cases where it's going to be particularly interesting. Now we're going to note what this means. If that R is actually a constant, and it may not necessarily be a constant depending on the material, but if it's a constant, then if we double the potential, if we put a 6-volt battery across this if we put a 6-volt battery instead of a 3-volt battery, then the current must naturally double as well. The greater the potential difference, the greater the current. The resistance, that thing R, is measured in units of ohms. This is named after Georg Ohm. 1 ohm, we use a capital Greek letter omega to symbolize an ohm. 1 ohm is equal to 1 volt per amp. So an ohm is a resistance that must exist when a 1 volt potential difference produces a 1 ampere current. Okay, now when we think about resistance in circuits, we're going to generally consider the resistance to be localized in circuit elements. So that I might have a light bulb acts as a resistive element. There are actually elements called resistors, and we will see those in lab, and we will of course talk about them in examples here. Now, as we do this, one of the things we find out is that the resistance in a conductor is very, very small. It's very, very close to zero, so that it's very easy to think of that resistance to current flow and really strongly localize it to these discrete elements. So realistically, there's resistance spread all throughout a circuit, but the real resistance is going to live, for all intents and purposes, in one element. So if I come back to that picture way back over here of our battery and our light bulb, we're going to assume, for the most part, that that the wires here have zero resistance, the battery effectively has zero resistance, all of the resistance is tied up in that light bulb. And that actually is a fairly representative statement. It's not completely true, but it's fairly representative. All right, so let's do a little calculation with this. A person might experience a mild shock if the current along a path through their thumb and forefinger exceeds about 80 microamps. We'd like to compare the minimum potential difference necessary for such a shock under dry skin conditions. Now, when your skin is dry, the resistance of a path like that from forefinger to thumb, how many of you are looking at your forefinger and thumb right now? The resistance of that path might be on the order of 400,000 ohms, 4 times 10 to the 5th ohms. When the skin is wet, that resistance will drop by a factor of about 100 to about 2,000 ohms, or 2 kilo ohms. All right, so we'd like to see what potential difference will produce that kind of current in each of those circumstances. All right, we've got a target current, that 80 microamp mark that we're trying to determine, and we have two different resistances. We're going to use Ohm's law to calculate those two. Why don't you go ahead and take a stab at that right now and figure out what potential difference we need in either case. All right, hopefully you've solved those. Let's take a look at the solution now. We're going to use Ohm's law, delta V equals IR. For dry skin, we can take that current and the dry skin resistance, and we find a potential difference of 32 volts, a fairly sizable potential. On wet skin, because the resistance is much less, the potential difference required will be much less, and so we end up with this potential difference of about 16 hundredths of a volt. A very small voltage will produce that shock condition. So what I want you to think about is if you've ever tested a 9-volt battery. A 9-volt battery is a little rectangular battery with the two terminals on one end. You may know that if you want to know if that battery is a good battery or if it's been depleted, one way to find out is to touch the two terminals to your tongue. Basically lick the terminals of the battery together. When you do that, if the battery is good, you'll get a little shock, and it's a nice little, well, nice is an odd word, but it's a tingling sensation. Just bordering on a little unpleasant. If the battery is dead, you feel basically nothing. Why does that work? When you lick the battery, that resistive path, because of the wet skin, that path has a very low resistance. If you take that same battery and just touch it to your hand, touch it to your arm, you'll never feel that tingle of that current. The resistance is too high. Okay, Now, that resistance is an extrinsic property. It depends on the material itself, and it also depends on the size and the shape of the material through which the current is flowing. The intrinsic property we call the resistivity, and we symbolize it with the Greek letter rho, and it has units of ohms times meters, ohm meters. The physical dimension characteristics that are important are the cross-sectional area A, through which the current is flowing, and the length of the path D. So the longer of a path that current needs to flow through, the greater the resistance is. But the larger the cross-sectional area, the less the resistance is. Now, just to give you a little bit of feel for what these resistivity numbers look like, good conductors, metals, typically have resistances on the order of 10 to the negative 8th ohm meters, so very small resistivities, and therefore some very small resistances. In a conductor, each atom basically contributes on the order of 1 to 2 electrons per atom in a metallic conductor. Other good conductors, ionic solutions. Ionic solutions have resistivities typically on the order of 10 to the negative 4th to 10 to the negative 1st. An ionic solution, of course, consists of positive and negative ions typically in an aqueous solution. Those ions can flow fairly easily from one place to another, but they don't flow as well as electrons in a metal. Now note, not all metals have resistivities that low. Metals such as tungsten, for example, it's used in a common incandescent light bulb, have resistivities on the order of around 10 to the negative 5th or so, I believe. Plasmas. So a plasma, as you hopefully know, is a very low-density ionized gas. They will have resistivities that are typically somewhat very close to the metallic conductor resistivities. So again, on the order of 10 to the negative 8th ohm meters or so. All right, so let's take an example here. We have 18-gauge copper wire, and it has a diameter of 1.024 millimeters. We'd like to know what the resistance of 15 meters of that wire is, given that the resistivity of copper is about 1.68 times 10 to the negative 8th ohm meters at 20 degrees Celsius. As we're going to see in a little bit here, resistivity does change with temperature. All right, so we know the resistance is related to resistivity through equation 5. So all we need to do is calculate that cross-sectional area and then calculate the resistance. Go ahead and try that out and come back when you're ready. All right, let's take a look at the solution. So the cross-sectional area of the wire is a circle, and the area is going to be pi r squared. And you might have already caught, as I just did, that I've got a little bit of a error in my slide here. I have a radius listed as 1.024 times 10 to the negative 3rd meters. I've cited above in the box in the question that that's the diameter, so I'm already overestimating by a factor of 4. So my number is going to be incorrect for the problem stated. I seem to do that a bunch. You'd think if I proofread this, I would have catch it beforehand, but sometimes proofreading one time is not enough. Let that be a lesson to you. All right, so let's ignore the numbers ignore that number for the time being. We'll note that the resistance then looks like the resistivity rho multiplied by the length in the numerator. There's our length divided by our cross-sectional area. And with this, it's a factor of 4 too big. I come up with a resistance of 0.0766 ohms, which should be a factor of 4 too small. So if you calculate with the correct radius, you should come up with something on the order of 0.29 or 0.30, something like that, ohms. So you can check and correct for my mistake. All right, let's try something a little bit different. We're going to take a wire of initial length L naught and radius R naught, and it has a resistance R naught, capital R naught. And we'll just give that a number, 1 ohm. We're then going to squeeze the wire. We're going to put the wire between some rollers, and we're going to squeeze it down until it has a radius of 0.25 R naught. So basically, we're going to cut its radius by a factor of 4. And we're going to find out what we want to know what the new resistance is. Again, if you'd like to try this out, stop before I go on to the next slide and take a look. All right, let's take a look and see what our approach is like. So here's the thing. We know that matter is conserved. We're not going to actually compress the copper. When we squeeze the wire, we are just redistributing the copper. We are not compressing it. So the total volume of the wire is going to remain constant. So really what we need to do is describe the current volume of the wire and describe the new volume of the wire in terms of a new length and a new radius, and know that those two volumes have to be equal. Matter is conserved. Again, take a moment, pause the video, and see if you can come up with an expression for the new velocity, the new volume in terms of the old volume. All right, so here's what I got. I know that these two volumes are equal, and I know that the wire is effectively a very long cylinder. It has a cross-sectional area that looks like pi r squared, and it has a length L. Originally, it had a cross-sectional area that looked like pi r naught squared and a length L naught. So if once we can cancel out the pi's from either side, and I'm going to take this r, the after r, I'm going to replace it with 1/4 r because we turn the radius from r naught to 1/4 of r naught. And of course, we square that. I'm going to leave my R naught and L naught over here just as they are. And I'm going to divide both sides by that 1/4 R naught quantity squared. All right, so 1/4 squared is a 16th. In the denominator becomes 16 in the numerator. R naught squared over R naught squared cancels out, and I end up with a new length that is 16 times the original length. So when I squeeze this thing down, decreasing the radius by a factor of 4, I must increase the length by a factor of 16. Okay, so let's calculate the new resistance. I know that the new resistance has to look like rho times L over A. So my length is 16 L naught. My cross-sectional area is pi times 1/4 R naught squared. So I end up with an L naught over R naught squared. This quarter becomes 16, or becomes a 16th, sorry. And that 16th flips up into the numerator so that we have a 16th, so we have 16 times 16 to give me 16 squared. So I have rho times 16 squared, L naught over R naught, and I see I've left off a square here, and I also left off the pi. So you can write those in place. It turns out this one actually won't affect the number in the calculation here. This I just left those two terms off in these two lines. Rho does not change. The resistivity of the wire has not changed. And so I'm going to take that, I'm going to group these things together. So I've got this 16 squared, which is 256, and I'm going to end up with rho times L naught times pi R naught squared, once we add those missing terms back in there. And that thing we will recognize as just R naught. Rho L naught over pi R naught squared. So my new resistance is 256 times greater than the old resistance. Well, that makes sense. Look, our resistance is greater for a greater length, and it's greater for a smaller area. And when we squeeze this wire down, we do both things. We get a greater length and a smaller cross-sectional area. And so we end up getting a much larger resistance. Okay, let's stop there. We're going to make this the first video of this group so we can sort of break this up into smaller chunks. Make sure you understand this material and then go take a look at the second part.